Good morning to all the attendants. I'm Peishan Zhou from Griffith University, Australia, and it's a great pleasure to present my work using UNets for accurate RPIC detections in fetal ECG recordings here at the 10th International Conference on Signal and Image Processing 2024. And our work will be presented through the following 4 sections. So to begin with, I will provide some background information related to our research work. So first we will talk about the electrocardiogram signals, which is efficient technologies could be used for monitoring and diagnosing conditions affecting the heart. It's important and really simple techniques could be used for long-term monitoring, and that's why it's quite a popular technologies we applied today. And we can see the figure here that shows an example of cardiac cycle of the fetal ECG signals. It includes 3 main features like the P-wave, and the QRS complex. All these features can be used for disease diagnosis. But for the fetal ECG signals, it's quite difficult to catch a clear features of the 3 or some of them, because the non-invasive fetal ECG signals is a mixture of the maternal ECG and different type of noise we can see here. So the fetal ECG is obtained by canceling the maternal ECG first and then remove the rest of the noise. And by doing that, the extracted fetal ECG is always quite weak and have a really low SNR levels, and also may have morphology distortion. And in that morphology, the RPIC has clearly the highest amplitude, which is make it most obvious peak in the fetal ECG signal. But so the accurate detection of the RPICs is essential for analyzing things like QRS complex, fetal heart rate,
Yeah,
and
patient,
also, yes.
your slides are not moving.
Uh, okay, so which page are
Yeah,
we
yeah,
now?
yeah, fine.
You say it's moving now?
No, it's not moving still.
Are we in the clinic significant of RPIC
Yeah,
detection?
I think you can just stop sharing and again start sharing your screen with a screen slide option.
Okay.
Yeah.
Um,
Yeah, it's moving now. You can go ahead. Patient, it's moving. You can go ahead.
all good now?
Yeah, it's okay, fine.
Yeah, okay. Thanks for telling me that.
Yeah.
So accurate detection of the RPICs is quite essential for analyzing the QRS complex, the fetal heart rate, and also this heart rate variabilities. And all these informations have been proven to be the basis for early detection of many diseases related to the fetal and also the maternal. So accurate detect RPIC can provide significant clinical information we need, and it can be used to making more timely decisions. And as we mentioned before, the fetal ECG are obtained by canceling the maternal, so the extracted fetal ECG are always weak and sometimes comes with morphology distortion. And currently, we have RPIC detection methods like Tompkins algorithms are not designed for the fetal. So it will have more both detections when we apply that technical to the fetal ECG, because the fetal have a really low RSNR level. So we can see in these traditional methods, they have applied several steps of filtering to reduce the noise. But when we do this to the fetal, it will cause more information loss because it will distortion the morphology furthermore. And secondly, the morphology of the fetal ECG is quite different from the adults. And the parameters we use here, like the threshold 1, threshold 2, are designed based on the adults. So the current detection methods doesn't work so well with the fetal. And that's why we want to propose something to achieve an automatic RPIC detection algorithm for the fetal ECG signals. And the deep learning technology uses artificial neural networks as the architectures, and it can be used to achieve things like results detections, classifications, and predictions. And we think these methods could be used for our research aim. And this UNet structure is one of the deep learning model, which has the encoder-decoder structures. It contains symmetric passes, which will like benefit the capturing context, and this escape connections in between will help with overfitting problems and make this more effective for research work only with limited training data. And all this make it a quite potential structure for the task of like strong robot RPIC detection. So we are aiming to propose a novel algorithm to enhance the fetal RPIC detection algorithm itself. So thereby can improving the accuracy and reliabilities in detection RPIC from low-SNR fetal ECG signals. And this algorithm should be able to provide robust RPIC detections even with fetal ECG signals have low SNR level and signal distortion. So this figure shows the scheme of the proposed fetal RPIC detection methods. You can see that we have like 3 stages for this method. The first one is data preparing, which will process the raw signal to make it suitable for the proposed model training. And the second stage is model training, and then followed by stage 3, which including additional post-processing steps to identify and eliminate false positive predictions, and thereby enhancing the accuracy of the RPIC detection furthermore. First, the 1 kHz fetal ECG signals will downsample to 50 Hz. And this is because the low sampling rates are sufficient or more clinical applications and more practical in terms of data storage and processing requirements. And then followed by a post-train map will be generated based on this true RPIC annotations provided from the database. And each post shares the same Ys and being centered on the RPIC position. And each post is labeled as a series of ones. And the rest of sample points were labeled as a series of zeros. And in this study, we set the post-wise to 15 sample points because from the series, this wise kind of shows the range for the QRS complex. And the last step is segmentations. We use a fixed sliding window of 1,000 sample points, which equivalents to like 4 seconds long signal range. And the shift update for sliding window is set to 200 sample points for this work. And here we show the structure for the proposed UNet model for training. Yes, as we mentioned before, we feed the model with the fetal ECG signals, and we train the model use this expected output feature, which is the post-train map. The proposed ECG signals sent to the UNet through the encoding stage, and the output of the 1D convolutional layer is saved before going through the max pooling. then followed by the decoding block to achieve the upsampling process via the transpose convolutional layer. And the output of the transpose convolutional layer is skip connected with the output of the 1D convolutional layer in the encoding stage as well. Finally, the model's output feature is a post-train map representing the predictions of the potential R peak
Patient,
locations.
again, your slides are not moving. It is in the fifth slide.
How about we just keep this?
Yeah, now I think you can click on the slide. If you're going to the next slide, just click on your slide and then you can go. Okay, now it's in 13th slide. You can go ahead.
Oh, okay. Is it changing now?
Yeah, it's visible. It's okay now. You can start.
Here we show the stage 3 that the model's output then undergoes additional post-processing steps. We first convert back to the full length through the overlap as methods. Then we apply the first threshold to remove potential false positive predictions where the amplitude of the output post-train are too weak. And by this, it means the prediction values below the threshold we set will be converted back to 0 and the rest will remaining 1. So we can see this example here. This is the output of the model. After the first threshold, we remove this potential bits because it have a really low amplitude. And after that, the middle value of each post is taken to generate a R-peak series corresponding to the predicted R-peak locations. And finally, a second threshold is applied to eliminate potential bits that are too close to be physically possible. So in this work, we use Abdominal direct fetal electrocardiogram database. This is because it provides direct fetal ECG, which can be considered as an extracted fetal ECG from the mixture. And the data also provided the RPEAK annotations for 5 records from 5 different subjects. And each recording lasts for 5 minutes, sampled at 1 kHz. 3 metrics are used for model evaluation, and a matching window we show here is used to decide whether the prediction should be considered as a true positive or false negative or false positive. When the prediction is set within this matching window, it will be considered as a true positive or a false positive predictions, depending on whether there is a true R-peak. And it will be considered as a false positive if the prediction is outside this matching window. So we trained the model for 400 epochs. We performed interpatient testing scheme and 5-folder cross-validation, which means the training data won't be seen with the test data. And we also implement 2 Pentamkin-based baseline methods for compare. And it can be seen from the table that our proposed units achieves perfect score of 100% accuracy for sensitivity, PPV, and also F1 score on 4 records. And it drops a bit for record R10 is because we got 5 false negative predictions. And these 5 false negative predictions could caused by the angular large regions in the original database. It means that there's no bits in this area and there's no fetal ECG signals showing up. And this is probably caused by the signal loss or the poor connections between the electrode we placed on the belly. And if we see the results here, you can see the traditional methods, Penn-Tompkins, do have more false positive and false negative predictions, which, as we mentioned before, and that's the reason why we want to propose a new algorithms to suit fetal ECG more. And table 4 here shows the average results in terms of three metrics between these three methods, and it's clearly that the proposed UNet architectures achieve the optimal performance over three methods. Here we do want to mention the proposed UNets also shows an improved resistance to noise. And here's an example showing a noise spikes exist in that record R08. So for this alveolar morphologies, two traditional methods do wrong predictions or even miss the beats. It's like for this PTAE methods, if do the wrong predictions and also miss the true beats here. And for the second methods, you have the true beats over here, but it also influenced by the spike and make one more false positive predictions. But our units are quite robust to the alveolar morphology, and we are all good with this thing. So overall, this works definitely novel application to achieve R-peak detections, especially for the fetal ECG signals. And we have achieved a high performance with three metrics and have an average F1 score of 99.91%. And also it was mentioning that the we have less false positive, false negative predictions than the traditional methods. And in the future, we are trying, we're gonna have more experiments running with different database and also try different type of noise and level of noise distortions. And we're also gonna evaluate the model's computation complexity to make them suitable for the real-time use. Yeah, and I think all the results will go into the following journal sections. Yep. That's all for the works we done for this UNES things. Thanks everyone. Yep.